I have been studying the Mandelbrot Set since 1985. Back then, all I had was a Commodore 64. As far as I know, no one has studied the Mandelbrot Set more extensively than I have. And no one, and I mean no one, is claiming that the Mandelbrot Set is a black hole, except for me. The motivation for my research is plain and simple. I want to understand the universe. I don't really care who's right, but I tried to understand relativity, and I tried to understand quantum mechanics. I made my best effort, I really did, but I kept hitting a brick wall. Something did not ring true to me. In the end, I had no choice but to do something completely different. My name is Lori Gardy, and I am a critical thinker. Black holes are of the most mysterious objects in the universe. Consensus is that black holes exist in nature. Consensus is that black holes are an important feature of our universe. Fractal geometry is equally mysterious and equally important. And since fractals appear just about everywhere in nature, it seemed reasonable to wonder if the Mandelbrot Set itself might also appear somewhere in nature. The main property that distinguishes fractal geometry from other geometries is the property of self-similarity. The extreme scalability of black holes was my first clue that black holes have the property of self-similarity. We have massive black holes at the stellar scale, we have supermassive black holes at the galactic scale, and so on. This is what ultimately led me to the quasi-black hole analogy that I'm presenting here today. This analogy also leads to an alternate description of time, space-time curvature, and black hole entropy. The purpose of this research is to see how far the black hole analogy can be taken. The main question is, could there be a mathematical model other than relativity that mimics the behaviors of black holes? If so, can this model make a prediction? And if it can, is this prediction testable? It turns out that quasi-black holes, as outlined in this video, does lead to some interesting predictions that differ from standard thinking. One of the main objections to this body of work is that it does not cite the many successes of general relativity. Aside from comparing my Mandelbrot Set model to the Schwarzschild black hole, this mathematical model doesn't look anything like relativity. Here's a thought experiment. What if relativity never existed? Would we all be living in the dark ages because GPS wouldn't be working properly? Would we all be lost if Einstein's relativity was never invented? What if fractal geometry predated relativity? Could we still have intuited the existence of event horizons and black holes? Obviously, I believe the answer to this question is a resounding yes. First, let's talk about complex numbers, since the Mandelbrot set literally lives in the complex plane. Complex numbers are two-dimensional numbers with one real component and one imaginary component. The origin, or 0, 0, of the Mandelbrot set is the origin of the complex plane, which is here. Another complaint about my approach to black holes has to do with dimensionality. How can a 2D static mathematical object possibly describe the 3D dynamic universe that we observe? First of all the 2D complex numbers can be extended to 4D using quaternions. Here, Instead of one real and one imaginary component, we have one real and three imaginary components, I, j, and k. Technically, the two-dimensional Mandelbrot set generates a one-dimensional complex curve as depicted by the fuzzy white boundary surrounding this image. In a similar manner, the four-dimensional Mandelbrot set would generate a three-dimensional complex curve. This, I argue, is what we perceive as the curvature of space. In the standard model of cosmology, space and time are combined into a four-dimensional space-time manifold. Space-time curvature is often explained using a bowling ball and a trampoline like this. This, however, is a poor analogy as it is using gravity to explain gravity, but that's not my problem. In the model I'm proposing, the manifold of the universe is complex. That is, it is mathematically modeled using complex numbers or quaternions. In this model, time is not part of the manifold, but is something completely different. In the model I am proposing, time is decoupled from the concept of space. Here, time is merely an emergent property of change. The assumption here is that without change, there can be no concept of time, and therefore no arrow of time. In the fractal paradigm, iteration is the agent of change. Iteration amounts to a transformation, and transformation is a fancy word for change. Therefore, iteration is an analogy for time in this model. Iteration generates change, and change gives us the sensation of time. Since time is not a location that one can return to, modeling it as a spatial dimension gives the false impression that one can go back in time. In the model I am proposing, iteration is the agent of change, and iterative change cannot be undone. As one cannot unbreak a glass or unborn a baby, one cannot undo iterative change. This leads to a clear understanding of entropy as irreversible change. Here, entropy literally means that change cannot be undone. In fact, when all of physics is defined in terms of change, things become quite simple. Inertia is resistance to change. Time is an emergent property of change. And entropy means that change cannot be undone. With that out of the way, let's get back to the Mandelbrot set. Here, I will briefly outline the methods used to generate the Mandelbrot images presented in this video. First, we select an initial point, or a seed point, from somewhere in the complex plane. Let's call this C. Here you will see that x is the imaginary component and y is the real component. We then initialize a variable, let's call it z, to this seed point, z equals c. Next, we iterate the function z equals z squared plus c, which generates a new complex number. This new complex number then gets stored in a list. I refer to this list as a trajectory. Finally, we replace the old z with the new z, and we do it again. Each point on the complex plane generates a different set of points, or trajectory, and each trajectory has a unique behavior. When plotted directly, each trajectory paints a different picture. This algorithm divides the complex plane into 3 domains. The outer grayscale region corresponds to the domain of divergence. These are the seed points whose trajectories diverge past the boundary condition after a finite number of iterations. The inner black region corresponds to the domain of convergence. These are the points that never escape the boundary condition even after an infinite number of iterations. Instead, they converge towards one or more singular points within the complex plane. Exactly between the diverging and converging domain is what I refer to as the domain of uncertainty. This is represented by the bright halo surrounding the black region in this image. These are the seed points that take a long time to decide which domain they belong to. Remember, time is analogous to iteration in this model. Next, we are going to talk about the anatomy of the Schwarzschild black hole, and then we're going to compare it to my MSET model. The main features of the Schwarzschild black hole include the black hole singularity, the event horizon, and the lesser-known photon sphere. A black hole is a theoretical region of space where space-time is curved so much that not even light can escape. The event horizon is the theoretical boundary beyond which nothing can escape. The radius of the event horizon is referred to as the Schwarzschild radius. At the very center of the black hole is a region of space that is infinitely small and therefore infinitely dense. This is referred to as a singularity. The lesser-known photon sphere is a region of space just outside the event horizon where photons are forced to travel in complex orbits until they ultimately escape the photon sphere boundary, 3gm over c squared. Now I will show you the correspondence between the Schwarzschild black hole and the MSET quasi-black hole as outlined in this video. The black hole singularity is mapped as follows. The photon sphere and the event horizon. The main difference between these two black hole models is the shape of the event horizon. The Schwarzschild event horizon is a clearly defined spherical boundary with one and only one Schwarzschild radius. The Mandelbrot Set event horizon is a fuzzy boundary with an infinite number of Schwarzschild radii. Also notice that the region surrounding the quasi-black hole is slightly pear-shaped and offset from the center of the photon sphere boundary condition. This is an important feature of the quasi-black holes, as you will see shortly. So, why do I make this correspondence? What evidence do I have? To begin, let's look at a single point from the complex plane as shown here. On the left is the black hole region of the Mandelbrot set. Remember, these are the points whose trajectories never escape even after an infinite number of iterations. The figure on the right shows what happens when you iterate them through the function z equals z squared plus c. Here is the seed point. The next point is the first iteration, then the second iteration, then the third iteration, and so on. As you can see, this trajectory appears to be getting closer and closer to some point within the complex plane. Also notice that with each iteration, the distance between the points gets smaller and smaller. Although you can't see it, this shrinking continues for quite some time. In order to see this, we need to shrink the measuring stick or pixel of the image. What we are seeing here is the continuous collapse of that trajectory towards some very small region within the complex plane. Due to the limit to the digits of precision of the computer, this collapse eventually breaks down. This is an important point, which we will talk about later. Now I'm going to show you what is happening mathematically. On the right, you will see the same animation from the previous slide, and on the left is the numerical value of the seed point or starting point before any iterations. Notice that this point is displayed to 17 decimal places. This corresponds to the digits of precision of the computer I was using. Now, I'm going to start the animation, but here I want you to pay attention to the digits on the left. Notice how the digits to the right are changing quickly, while the digits to the left are stabilizing one at a time. Basically, what is happening here is the iteration process is shrinking the trajectory to a smaller region within the complex plane. This requires more digits of precision. At the end of this animation, you will notice the breakdown of the collapse. This is happening because we ran out of digits of precision. If we had more digits, then the collapse could continue. Given an infinite number of decimal places and an infinite number of iterations, the collapse could continue indefinitely. In my model, these infinitely collapsing trajectories are analogous to the infinitely collapsing singularities of relativistic black holes. As I said before, each point on the complex plane generates a different trajectory, and each trajectory makes a different picture. Here are a few examples. Keep in mind that each of these figures was generated from a single seed point from the complex plane. It was found through experimentation that the seed points closest to the event horizon take more time to collapse to singularity. The pictures they paint are also much more interesting. It was also found that some of the seed points generate more than one singularity, as you can see in this image in the center. Next, we're going to have a look at the trajectories from the photon sphere of the Mandelbrot set. These are the seed points from the complex plane whose trajectories can and do escape the boundary condition after a finite number of iterations. For the sake of the discussion, I simplified the figure to only two regions. The outer gray region corresponds to one iteration. The next inner gray region corresponds to two iterations, and so on. As you can see, each iteration brings us closer and closer to the black hole region of the Mandelbrot set. In the black hole region, each iteration brings us closer and closer to the photon sphere. This is an important point. Both the inner region and the outer region exhibit this behavior, which I'm referring to as asymptotic behavior. In the Mandelbrot set quasi-black hole, we see asymptotic behavior on both sides of the event horizon. Here, I argue that the same thing is true of cosmological black holes, that they experience asymptotic behavior on both sides. Put simply, it is just as hard to get into a cosmological black hole as it is to get out of one. This is a huge departure from the relativity that claims that it's easy to get into a black hole but impossible to get out. Is there any evidence of this, though? According to a study by NASA via the Chandra X-ray telescope, less than 1% of the material initially within the gravitational influence of the black hole reaches the event horizon or point of no return. Most of it is ejected. If it were easy to get into a black hole, then you would think that anything that gets close to the black hole would fall in, but this is not the case. Very little material actually falls in. Most of it gets shot out as jets. We don't even know for sure if anything actually falls into a black hole. Some of the material could get caught up in the photon sphere and then shot out much later through the jets. Asymptotic behavior on both sides of the event horizon is the signature of a quasi black hole. Relativistic black holes do not predict such a thing. Here are a few samples of the trajectories from the photon sphere of the Mandelbrot set. The images at the top are real cosmological objects. Below each of these is an M-set trajectory that is very similar, self-similar, to the objects on top. We have the Cartwheel Galaxy, the Stingray Nebula, Cat's Eye Nebula, NGC something or other, and Einstein's Cross. Einstein's Cross is the most controversial. The appearance of Einstein's Cross is thought to be caused by gravitational lensing. This, of course, is only a hypothesis. No one really knows for sure why this object looks this way. The only way relativity can explain the appearance of this object is via gravitational lensing, and even that is a bit of a stretch. If fractal geometry and the Mandelbrot set had predated relativity, then an object such as Einstein's cross would not have been a big surprise. Here is another example of a photon sphere trajectory. On the right is the Virgo cluster. On the left is a Mandelbrot set trajectory from the photon sphere. I want you to pay attention to the doubling up of the objects within these images. These two images are morphologically very similar. More similar than any simulation that relativity can come up with. What are the implications of this? According to the theory I'm proposing, objects like this were born this way. The event horizon of the Mandelbrot set is the key to understanding quasi-black holes. The event horizon is a domain separator. It separates the black hole from the photon sphere. As I mentioned before, there is asymptotic behavior on both sides of the event horizon of a quasi-black hole. The most interesting thing that I discovered while studying the Mandelbrot set is the morphological similarity between the M-set trajectories and some of the well-known cosmological objects that I showed you. Let's have a look at a few more. Keep in mind that each of these was generated from a single seed point from the complex plane. Next, we are going to talk about gravity and the curvature of space. If we simplify all the forces, including gravity, to the concept of the gradient, then it is easy to visualize the curvature of a manifold of space. Just think about topological maps. The image on the right can be considered a topological map of a zoomed-in region of the Mandelbrot set. Notice how the lines of the gradient get closer and closer together as you look closer to the black hole region. Remember, the closer we are to an event horizon, the more iterations it takes to resolve the points. In a topological map, when the lines are closer together, it means that the gradient is steep. When the gradient is steep, it means that the force, let's call it gravity, is greater. The Mandelbrot Set algorithm is actually a curvature generator. It represents all the ways that space can curve. Here is another way of depicting the curvature of space. The image on the left is a subregion of the Mandelbrot set. Here, the bright regions correspond to regions of high iteration. In the Mandelbrot set, the regions of high iteration correspond to regions of extreme curvature. The image on the right is a picture of the grand spiral galaxy. Here, the bright regions correspond to regions where matter is clumping. Where there is matter, there is space-time curvature according to general relativity. Notice that M set curves the space in a similar manner, self-similar, to how nature curves space. Another interesting topic has to do with the various kinds of symmetry found within the Mandelbrot set. First of all, you will notice the obvious left-right symmetry of the black hole region. You will also notice that far away from the black hole, the symmetry changes to a different kind of symmetry referred to as chiral symmetry. In general, a chiral object is an object that is not superimposable on its mirror image. Chiral symmetry is commonly seen in the spiral arms of galaxies as seen here. Spiral arm-like phenomenon can also be found in other regions within the Mandelbrot set. Although I have a lot more to say about this, to save time, I will leave it to the reader to read this section on my paper, The Mandelbrot Set as a Quasi-Black Hole, which is linked in the description. Suffice it to say that this may be related to the chiral symmetry breaking that you often hear about in physics. I also said earlier that my black hole analogy leads to an alternate description of black hole entropy. Again, to save time, I will leave it to the audience to read this section in my paper. In short, black hole entropy, as defined by Bekenstein and Hawking, states that the area of a black hole event horizon must always increase over time. It can never decrease. Using Euclidean geometry, the only way that the surface area of a spherical object, such as the Schwarzschild black hole, can increase over time is by increasing the radius of the object. Fractal geometry, however, offers another way for the area of an event horizon to increase over time. According to Benoit Mandelbrot's "How long is the coastline of Britain?" hypothesis, the measurement of the coastline will increase when you decrease the size of the measuring stick. This is true for all fractal objects. I tested this myself, and it is true. This idea leads to an alternate explanation of cosmological redshift and the accelerated expansion of the universe. Again, you can read this section in my paper for more details on this subject. So the question is, do quasi-black holes exist in nature? We already saw the Mandelbrot set is able to generate trajectories that are morphologically very similar to some cosmological objects. Interestingly, the cosmological objects that the Mandelbrot set mimics also happen to be associated with black holes. Here I want to point out that the background image that appears in all my slides was also generated using the Mandelbrot set. The question is, can this model make a prediction? And if so, relativity predicts that the black hole at the center of our galaxy will look something like this. And I predict that the black hole at the center of our galaxy will look something like this. Very soon, we may be able to determine what kind of black holes nature actually makes. The Event Horizon Telescope is a radio telescope array that spans the entire Earth. The aim of this telescope is to observe the environment surrounding the massive black hole at the center of our galaxy, as well as the larger black hole in the galaxy called Messier 87. The angular resolution of the array is comparable to the black hole event horizon, and so they are hoping to be able to resolve the region surrounding these two black holes. They are also hoping that this experiment will confirm relativity yet again. I, of course, am hoping for something completely different. The telescope array was up and running and collecting data in April of 2017. The data should be available to the public sometime in 2018, literally any day now. Luckily, we don't have to wait for the Event Horizon Telescope results to test my hypothesis. Messier 87, or M87 for short, is a supergiant elliptical galaxy in the constellation of Virgo. It was recently discovered that the supermassive black hole at the center of this galaxy does not currently reside at the gravitational center of its host galaxy. Instead, it is 22 light-years away. Notice that the bright region surrounding the black hole is not circular, but instead is slightly pear-shaped. Interestingly, when you register the Mandelbrot Set model with this bright region, you find that the location of the black hole corresponds precisely to the origin of the complex plane. This is the only point in the complex plane that does not generate a trajectory. Technically, this is the point of stillness. In other words, the black hole singularity is exactly where it's supposed to be according to the Mandelbrot Set model that I am proposing. I agree that this is highly speculative, but interesting nonetheless. Here is another example. On the left is a picture of the galaxy 3C 186. The bright flare in this image is the giant quasar associated with this galaxy. Like M87, this quasar is found to be not at the center of gravity of its host galaxy, but is offset by around 35,000 light-years. Again, we see a pear-shaped region, and again, we see that the quasar is exactly where it's supposed to be according to my Mandelbrot Set model. So what does all this mean? When the data from the Event Horizon Telescope is released to the public, I suspect that they are going to see something that they didn't expect to see. If they see anything other than a spherical region surrounding the black hole, such as a pear shape predicted by my model, this will be very difficult for relativity to explain. I am hoping that the release of this data vindicates my quasi-black hole model. This, however, will not be good news for the relativists. And now, we wait.